Okay, hi. My name is Chris McNamara. I'm here with my colleague Dave Hunt. We're in Intel in the software group. We're speaking on behalf of the team. Liang is here. Liang, you can put up your hand. You're also throwing out loads of work here. Radu and others. But what we're here about today is continuing the journey that we've been on to make DPDK green. And we're going to have a quick look over what we've done and how it's applied and what we're planning to do in the future. Really, what we've kind of learned as we've gone along that we're facing in a 100% polling environment, different types of challenges. And some of those, I think, came up at the summit here last year that we're going to go through about how do you trigger the state change for power, how do you get your system into an energy efficiency use case when you're quiet to a performance mode when you're busy, okay? Seems straightforward, right? And then we're going to talk a little bit about the configuration and how we apply those policies. So we're going to try and take you through that journey today, and hopefully it'll give you a good understanding of where we are and where we're going. Okay, excuse me. So what we're looking at here is a kind of a high-level mapping of where DPDK APIs and sample apps for power apply today, and some examples of the work that's been pushed onto the mail lists and is on the main line. What you see on the right-hand side is application that may take advantage of libRT APIs. And what we've added over the years are the ability to scale frequency, to turn on turbo boost, and provides those hooks to an application where, you know, is requiring to change state. So as an example, if you're quiet at nighttime, your application has the ability to turn down the frequency and save energy and save power. Or if you're busy, you can increase the frequency. For those of you that are familiar with a turbo boost feature that's in the CPU, it gives you more frequency. Now, on top of that, despite those basic capabilities, we've pushed examples as sample apps that allow you to configure the system for time of day, configure the system for packets arriving during that time of day. So we've put some examples that allow the system to scale down and scale up. So you can use those as building blocks. The packet arrival rate is interesting because it provides a trigger other than just setting the system up for, you know, nighttime be quiet, daytime be busy. Now, as you kind of map out the other pieces of this architecture, you can see from a virtual machine perspective that you also have those controls. However, the ability to change state when you're virtualized, it takes a lot longer. It's a slower reaction time. So if you're turning down your system and you want to scale up very quickly, then we introduced what you see here on the right-hand side, which is sample policy. So we changed from an architecture to have a policy delivered to what's shown as a VM Power Manager. Okay? So these are the building blocks that we've pushed and are available today. You'll see those in the sample apps and sitting around the libRT Power APIs. Now, one of the reasons we switched from what's shown the direct control from virtualized is that reaction time, but also it's a shared platform, it's a shared resource. You want to be able to provide a policy to this VM Power Manager, and this VM Power Manager could be seen as a brain or the piece that's applying power on behalf or for the entire system. Now, these are all the combinations. I want to be clear that you wouldn't necessarily put all these together onto a system at the same time. They're choices and options that you have, okay? Now, the last piece, and it's kind of shown on the left here, and you'll see it in a sample app, is what we had called packet arrival rate, which reads the NIC stats, makes an assessment of the rate of arrival of those packets, and this is used as a mechanism to figure if you're busy or idle, okay? So that's kind of what we have today, and as we enhance that as we go forward, here's a summary of some of the reasons that we pursued this architecture. One of the things that we found, and I'll just call out, is that the existing Layer 3 forward power does a great job of energy efficiency. However, it doesn't do as good a job as some of the newer mechanisms in terms of packet loss and in terms of latency. So this tends to be a starting point for a lot of developers and something we're going to try and address either through documentation or updates to that app. When we go from, you know, that was, I suppose, what we would call the original architecture that was used for the power management, and we've introduced these new mechanisms. Okay, now that's kind of a quick scan through what we have today, and as we move forward, myself and Dave are going to talk through pretty much 3 new capabilities or new trigger mechanisms. And I think this came up with the summit when we were here last year, was, how do you tell how busy you are? How do you know in a 100% busy environment, if you're shoveling 3 packets around or shuffling 1,000,000 packets around? So we put some time into figuring out how you would implement this in the architecture that we have. Okay. Right. So this is where it starts getting interesting. That's kind of landscape. And when we start looking at 100% busy cores, and we start looking at pole mode threads, we just took a graph here which shows a trend. On the vertical, you have the number of poles, and on the bottom, you have traffic. So Liang has pushed patches this week that support this use case, which we'll talk about in the next foil. What we were trying to achieve is to figure out how busy we were. And we spent a lot of time prototyping this, and we looked at things like crypto. So if you have a 1K packet, and we were calculating, OK, this is a 1K packet, this is the cycles per byte, how much work does it cost? And as the traffic type varied and different types of frames, we ended up in a situation where we were dimensioning our system for the worst case, which wasn't the most efficient. If you have to calculate for every frame how busy you are, you're just making yourself more busy. So we took another approach, which was essentially looking at idle. It was kind of like Matthias's, I think, touched on this a little bit, busy idle presentation yesterday. What we looked at was, if you could calibrate the system based on the number of times you read the queue and you got nothing back, if you're doing that all the time, you're obviously idle because there's nothing happening. You're not getting any frames into your system in a simple world for a PMD. So what this graph is trying to show is over 3 frequencies that if you took a base system and took 2 gigahertz, that you would get a certain, I think, of a few million idle poles. And at a medium frequency, you get the same. And at a low frequency, you get the same. So what we were trying to figure was, instead of trying to calculate the work that we need to do and how many compute cycles and adjusting the frequency to match that to save energy, if we took a view on idle, would it help? And this graph, what it's showing is that as our system got busier, we were getting less empty poles. So as the number of empty poles, we'll take a simple case. If you had 1,000,000 empty poles when you started your system, as you start getting busier, that trends towards 0. Then in our test case, we started seeing loss when that trended to 0. So for us, what it meant is, and this, I was going to say vertical, but it's kind of thrown up there. But if you start looking at this from an empty pole perspective with a threshold, you can start thinking about how, as your system, as the number of empty poles trends towards 0, that you could make an energy efficiency decision based on that. Okay? So as an example, if your threshold was going back and the number of empty poles was increasing and you were getting up towards your maximum available empty poles, you know that you're idle. So you could, in a sense, you could turn down the frequency, put somebody to sleep. So we're looking for triggers for energy efficiency or performance, conversely, as a way to manage the power better based on demand in the system. Okay? So one of the things you can do here is, you have an action. And what this line was intended to show was that as you trend towards 0, you could possibly turn on turbo with the DPDK API on the core, which would give you more frequency. So if you're heading towards a congestion situation, you could boost your performance. And conversely, when you're heading towards idle, okay? So this is one of the prototypes that we had. And what we tried to do is, we pushed some patches. And Liang has pushed these onto the mail list, and you can see them up here. But what? Did someone throw something? So what you can see here is, on the left-hand side, if you were to start implementing that scheme, we broke it down into a few high-level stages. We broke it down into initialization. So as you start your PMD, how many poles can you do? So you're calibrating against the frequency that you have, okay? So you know your worst case or your best case poles. And when you're running, as we saw in that previous graph, you start counting the empty poles, and you're checking against that threshold, okay? So as you get busier, your empty poles goes to 0, and you can adjust your state based on that, okay? So this is the general flow that we look to push with these patches, and we're looking for feedback and comments on them for 1811. So this was one of the kind of, I suppose, what we call traffic awareness, a very generic scheme that we could build on to make it easier to figure out when the right time was to change the power state of the platform of the CPU or DPDK application. Okay?
My turn.
Dave.
So that was one mechanism that we're in the process of developing, which is more in-band. So you instrument the changes in your application through the API that you had on the previous slide. The next one was another mechanism we were looking at, which is more of an out-of-band mechanism. If you have an application, you don't want to change your application, is there a way to monitor that application and detect if it's in an idle pole loop in the same way as the previous application, but out of band? So you want to detect the idle pole loop, and you want to detect whether it branches off into a different code path when it's processing packets. So I looked at various counters in the CPU to see, from one core, I'm looking at remotely looking at the other cores that are running the application, and I'm looking at the counters in those cores. And I looked at various counters, number of instructions executed, number of instructions retired. But the interesting one turned out to be branch hits and branch misses. And I looked at that and I said, okay, if we're in a tight loop, we're not doing many decisions as far as branches is concerned, or we're doing a fairly consistent rate of, the branch predictor will do a pretty good job of predicting where it's going next in that tight loop. But as soon as we get packets in, we're going to break out of that loop, process the packets, do whatever needs to be done, take whatever decisions and go on whatever branches we need to go on to process that packet, and then come back into that pole loop again. So it's an entirely different code path, so it's got a different ratio of branch hits to branch misses. So what we're looking at in the graph here is the ratio from 0% traffic rate up to 100% traffic rate. And we're looking at the ratio between hits and misses, and it looked like that it's fairly linear. If we start off at 0%, like when you're running that tight pole, the branch ratio is 0.01%. And when we look at 100% traffic, it shoots up to 4 or 5%. And it's fairly linear in between. When we take 50% traffic rate, we found that it was 2%, and 100% it's 4%. So if we took that that line, we could detect how busy we are. From a polling group, and this was against L3 forward, from 0% to 100%. So it's almost linear with traffic, with the traffic rate. So what we implemented in a patch, okay, we'll just talk about latency for a second as well. So what I was looking to see here was, did it have any adverse effect? Because I'm polling the branch radio mechanism is reading the core's counters every 100 microseconds. Now that's quite invasive into the remote core. So if there's 2 or 3 cores, I'm actually reading the counters of those cores with a tight thread, and reading those every 100 microseconds. But what I found was that if you take the maximum latency, or the best latency is down at this line at the bottom, that's when you're running 2.5 gigahertz. If you're running your core at 1 gigahertz, now this is an extreme swing between frequencies of the power saving, maximum power saving, we're running at 1 gigahertz. Obviously, your latency is going to be affected. But what we showed with the dark line down the middle was this is the branch ratio latency, so it falls within the 1 gigahertz and 2.5 gigahertz latencies, and they're max latencies. So what I was hoping not to see was the latency up here somewhere, that reading the counters would actually impact on the workload. But it turns out that it had very little impact on the workload. It's being absorbed into whatever else is going on in the CPU. So the max latency here, as expected, when we're running very low traffic, it's going to, or very low traffic, it's going to power save. So it's going to have your frequency down around 1 gigahertz. And then as you go up through, increase your traffic rate, it's going to be flipping more and more between, 1 gigahertz and 2.5 gigahertz until you get up to maximum traffic load. which is running almost all the time at 2.5 gigahertz. So the line kind of follows, as expected, the max latency, which was good news from my point of view, you know. So that patch was applied in 1808. It's in there. It's available for use. It's in the VM Power Manager. So you can run, because it's out of band, all you need to do is run the VM Power Manager with a list of cores that you want to remotely monitor. So if you've got a VM or a container or a host application that's running away as normal, unmodified on, say, cores 10 to 15, you can run VM Power Manager and tell it to monitor cores 10 to 15 using the branch monitor algorithm. And it will take over scaling up or down those cores depending on how busy that PMD poll loop or whatever poll loops are running on that core. It could also be used on any application, really, that's running busy spin locks. If it's running a busy spin lock and it's not doing anything, you can check out or measure your branch threshold by putting no traffic and then a lot of traffic through that busy poll loop or that spin lock. And when it breaks out of that spin lock, again, the same thing, it's a different code path, so your branch ratio will change. So you could use it for that as well. So have a play with that. It's in there in the VM Power Manager. So moving on to the final patch set. Now this is a patch set that's hopefully goes into 1811. It's up there. It was pushed up last week. Hopefully we'll have some review comments and discussions on it over the coming days. So what this is the current mechanism for what was added in, I think it was 1805, was the policy. No, it was actually earlier than that, 1802. We added policies where a virtual machine, rather than have direct control, and Chris mentioned the latency of getting a power command down through the Power Manager into the Linux governor, or down through the DPDK library to the Power Governor, there's maybe a millisecond or so of latency to get that command down. So to improve on that, we said, why don't we take the policy, send the policy down to this VM Power Manager, so then it has direct control to, you know, we saw in the previous slide measuring the NIC stats. So it has a much quicker access to the data that it needs to scale up and down, and much quicker access to the Power Governor rather than going through a VirtIO serial link. So it sends down a policy telling us which cores it's using, which NICs to monitor, what time of day possibly to go high or low, and so on. And that all comes down as a policy, and then it just forgets about power, and this takes over the power for that VM. But what was missing was that ability to do that same task for, say, containers or local host apps, you know, because it was limited to VirtIO serial communication. So what we've added in is this new link here through a FIFO, and it looks exactly the same to the VM Power Manager. We added in a new FIFO into the ePoll mechanism that's in VM Power Manager, so there's just another channel in there, and it looks exactly like the VirtIO serial channels in that it's receiving data on an ePoll, and when it gets an interrupt, it's all control paths. So when it gets an interrupt, it handles that event, handles the data coming in, processes it, generates the policy, and then starts looking after whatever cores the application has told it to look after. But instead of going binary, we added JSON, which has been mentioned several times before yesterday and today. So we added a JSON interface, which was a bit more friendly because this previous one was sending a binary structure down. So I said, why don't we send it in through a FIFO? So what that means then is that we've, as part of the patch, we have a couple of sample JSON files that you can send in a policy, and you can have a look at those, the JSON strings, edit them, send them in. It also handles all the previous power commands, like scale up, scale down, go to a particular frequency, all the commands that you could type in on the command line on the CLI application, you can also send through the FIFO, and there's examples of that in a little subdirectory called JSON examples. So now you've got a JSON interface into the VM Power Manager, and that will take over the power management for whatever cores this application is pinned to. So it opens up a lot of different applications to actually start pushing in power policies into into the Power Manager, and it was mainly done to support containers. Because, VirtIO serial was the limitation in the past. Anything else there can be used to access the FIFO on the host? No, I think that's it. So the patches that are pushed up last week are hopefully going to go into 1811. So as one of the changes in that was to allow the VM Power Manager to work without QEMU or any of that infrastructure installed, because sometimes when you're running containers, you don't want, the VirtIO serial infrastructure. We modified the application to allow without QEMU installed. And that then opened us up to just running the application as a bare metal application, just listening for the JSON strings coming in from the FIFO, and executing the power policies based on the JSON application. I think that's about it. Anything else?
No, just thanks to the guys who are acknowledged here, and Liang as well, who's been instrumental. The guys at the bottom tend to keep us on track to deliver something. So thanks to those guys for all their support.
So any questions? Question here, Mike.
In that container scenario, how do you decide what cores the container application can control the policy for?
Yeah. We would have, in the policy that comes down, that will tell us what cores are the pod. I'm not the expert on the container side of things.
The VM Power Manager can decide.
Now, if you switch back to that slide.
I was trying to go back. It's dead. Can you turn this on again?
No,
oh, yeah, there we go.
If that containerized DPDK application says reduce the frequency on CPU 1,
yes.
What prevents it from doing that?
When this container is dropped onto the system, right? The policy at that stage is sent through the FIFO into the Power Manager. Now that policy needs to contain which cores that application is pinned to. If it's a DPDK application, it's going to be pinned to cores on the system, right? So that policy the policy that comes down through the FIFO has an array of core numbers of APIC.
Sure, but that comes from an untrusted application.
Yeah, and that's what I was trying to get at, was the VM Power Manager as that central entity can decide to ignore or disregard that request from the container. So the policy would be, for example, at this packet rate, at this time of day, as a simple example, turn down the frequency or turn up the frequency depending on what's going on. So the VM Power Manager owns configuring the system.
So it needs to have access to some container manager to understand what cores this application can.
Yes, yes, exactly. Yeah. And that's to be provided via that policy. It's essentially a config.
Yeah, but it can't come from the DPDK application. It must come from something.
The container manager. In the case we're using this in a demonstration, that all the information from the policy comes from this third party. Now, there's another one of our colleagues working on that side of things. So they're actually using information when they're building this container to also, in parallel with that, generate a policy that contains the CPU. So they're providing this information down to the VM Power Manager.
Yeah, and our kind of abstraction for that was the config file. That's dropped by the pod manager and it comes to us. And then we read it in the Power Manager and apply it through the libRT Power API.
Again, that would be a very good question for the mailing list to get some discussion going. And if there's improvements we can make,
very good question,
feel
actually.
free.
Very good. Yeah.
So just repeat that on the mailing list and get some discussion going.
Okay, one of my other lives, and I have several, I work on network service mesh. And one of the things we're trying to do is to deploy NFV workloads in containers and in Kubernetes containers. So some of the core pinning and stuff are attributes that we have to manage. So I think we as a community would be very interested in talking to people from Intel and others that have some ideas about how, under the covers, what kind of mechanisms to do power and power management and CPU pinning and so on, container workloads.
Okay.
And that's a network service mesh.
Okay.
We'd be very interested in starting conversations around that, yeah, very interested.
what is the impact of reducing the CPU frequency in terms of power consumption? Is it linear or?
Close to, yeah, for the core.
For one core, okay.
Yeah.
Thanks.
You can test it with the DPDK APIs, the frequency scaling on your system, and that'll give you a much more accurate picture. And if you use turbostat and -- debug in debug mode, it will pretty much show you that straight away. You'll see the TDP for the CPU. So it's a fairly straightforward test case, so if you want to see. Yeah. Okay.
Yeah, yesterday we talked about defaults. What would you see that would be the smart default for Power Manager?
That's a good question. We spent a good while talking about that last night. I'm still thinking about that. I mean, by default, I think you'd probably see it off. In fact, you know, in general, when we go for DPDK sample applications, we're showing maximum performance. You know, when you're on an L3 forward, for example, that would by default have no power management. So we've created sample apps separate to those that if you're interested in saving power, you go straight to the L3 forward power application, you go straight to the VM power manager application, or you go to the power directory, and that's something we're thinking of refactoring within the DPDK sample applications, is refactoring all of those and maybe putting a power directory with all the power applications sitting underneath. So it's clear that, you know, when you're in there, you're dealing with power. If you're not interested in power, you know, go to the normal applications. Now, as far as like switching on something by default, I'm not sure. I think there'd be pushback from a lot of people, like if you start enabling power by default, because it does affect your latency. If you're changing your frequency, you're not able to handle as many packets, and then there's going to be, you know, latency impacts. Now, they're slight, but, you know, if people are going for the absolute best performance, then you want all your power management off. What we're trying to do here is introduce methods that can be switched on and minimize those impacts. You know, so there's always going to be trade-offs between power management. If you're, tolerant to, you know, latency and you know, that kind of thing, then you can enable power. But if you're not, you need it switched off.
I think it's a good question, because it depends on the application and the profile of the application, like you're saying. I would look at DPDK today out of the box as optimized for throughput and forwarding packets, whereas that's a flavor that might suit some applications, but if you have applications that are latency sensitive, you may want a different profile of DPDK. So I think it's certainly appropriate for power and energy, but I think that discussion widens the scope even to some of the default discussions that we saw yesterday. Is how are we going to define what default is? Is it, you know, latency optimized throughput? You know, is it high performance, which is, you know, typically a lot of power, high power, versus an energy efficiency approach? I think if we could bucket, you know, the default categories into 2 or 3, then we could see that configuration ripple through various DPDK components. So, but it's a good question.
There's also like with the Outofband method, the branch ratio method. I mean, if you're running a DPDK application unmodified, you know, that's your default configuration. If you want to apply power management to that, just start up the power manager with the branch ratio monitor enabled, and that will actually manage. Just tell it which cores to manage, and if it's a greedy application or a busy pole application doing very little, it will scale it down, you know, without changing the application. So that's another advantage of that. So if you want to use that method, that's there as well.
Yeah, just a question on the initial presentation, the first one. So as I understand, that needs to take like 5 seconds to run for that initialization stage to get the bands. Would it not be better to, I mean, do you think that's okay for an application that in the use case, and would it not be better to start with the top band, and if you can calculate from the amount of packets, you know, and then you can, if it's linear, you can maybe pick a band to drop down to?
Yeah, I think this is the piece you're talking about here, Kevin, is it? Where the
next slide, really.
Oh, next one, yeah.
It's not a init. The
init stage is too long, yeah, and that's fair, and we're looking at optimizing that. I think 5 seconds is long, especially for init, and we don't want to be extending that. One of the things we didn't really talk too much about here was that as you said, you might do the top band at initialization, but as your work changes, you may want to, what we had put in the README was training, but what our intention was that you would sample the system at various points of runtime so that you're recalibrating the number of empty poles because the work changes. And it's something that we need to look at to see is there a more efficient mechanism, I think.
Ideally, I'd like to see that a init section wasn't there, and maybe you could start at the highest power, and from the numbers of zeros that come back through the API, you can drop down.
Yeah, and what Liang and myself are discussing that very issue raised by yourself on the mailing list. We were talking about if there was a way just getting the frequency of the CPU for a typical application and just coming up with a sensible default. Rather than doing the training, there may be a method. We're actually looking at that to see if we could just ascertain that by reading a few counters, the frequency it's running at, and maybe working with the 50 cycle empty pole by default, and using that as a way to kick off the process, and then kind of training it as you go. That might be a better option.
So maybe it's 50 cycles into 2 gig, and that's our starting point as an example.
Again, it's a sample app. Therefore, we can look at it, improve it over time. Take that training out if it's possible.
In this particular one, and actually possibly in the other one, where you're trying to determine
הוא מתחיל להילחץ מזה. יש עוד כל מיני קייסים, דברים אחרים שהוא צריך לטפל בהם.
You're being translated in real time.
טוב,
AI.
Testing for just idle, or excuse me, empty poles. Did you look at how many packets you got on every pole? Because if somebody has a 32 entry list versus a 128 or 256 entry list, that would show a different scaling, right? And it may be you never get an empty pole because there's just enough trickle traffic to satisfy the counters. So I was just wondering if you had something satisfied for that.
What we tested this in a fairly consistent load was, I can't remember the rate, but it was a fixed packet size and a fixed rate. So you can see some variation. I don't recall that how it impacted this curve, but I would expect that you'd see some jitter in the curve when you see that little bit of burstiness. So it would come down to how you sample that emptiness and what you do after that. But
and as well as that, once you've done your initial training period, you kind of know what an empty pole looks like. You might never see empty poles, but you'd still be somewhere back over there on the curve, so you'd still be scaling down. You'd still be making some benefit out of the power management, even though you never hit empty poles. It's kind of designed to look, as with the branch ratio, it's kind of designed to give you a good sense as the traffic rate increases. It gives you a better idea of where you need to be on that curve, so you can scale down. And then when you get close to the zero, see, when you get close down to here, the idea is that rather than going on further here, you need to scale up, and then you scale up. So before you're getting down to this, packet loss situation, you're counteracting that. You're predicting, that you need to scale up. Yeah. Well,
okay, let's take it
All
offline.
right, sorry.
Yeah,
we'll talk after.
We'll save some time at the end for breakout sessions and
thanks.
stuff. So thanks very much, guys.
Thanks,
I appreciate that.